In this presentation, we want to look at a very useful data structure that uses something called hashing. It's kind of an odd name, but if we have an array it turns out that this array lookup, a sub 2, whether we want to add something to it or print it out, this process of looking up a value, indexing into an array is very fast. The computer can just simply calculate an address from the integer index and the array name, which is actually a pointer, the address to the first, so it can calculate the address of that location and access that extremely fast. One limitation on the array is that the index has to be an integer type or an integral type. It's not uncommon in applications to want to be able to map or store key value pairs where the keys are not integers but strings are one example. So for example, in this diagram we have different people's names mapping to maybe their websites. Currently, really the only way we know how to do that is by storing a linked list of key value pairs, and then given a key we can search through the entire list and try to find it. The downside of that is performance. If the list gets very large, we have to do a lengthy search each time, and that search, if there's no order to the list, that search will be a sequential or linear search, and that we know that that has n complexity. So we'd like to be able to do something faster that's closer to the array indexing, and this is where the concept of hashing comes in. In programming, this idea of a list of key value pairs is referred to as a hash map or a dictionary. In C++, they actually call it an unordered map. How can we actually do this? How can we try to take something like a string and convert it into a simple integer value to look up into an array? And that process is referred to as hashing. The basic idea is that we're going to make a hash table or a hash map or a dictionary, or in C++ they call it an unordered map in the standard template library. It's typically implemented as a dynamic array of lists. Sometimes you'll see the word buckets used. And so here's our dynamic array that has 7 values, and each element in the array is a list of key value pairs. And we somehow have to create a function that will convert the key into a number, and then we adjust that number so it falls within the limits of our dynamic array, usually with a mod operator where you mod it by the size of the array. So if we had a string for a person's name, maybe Andy, and we applied our hash function and we got a value of 17, and then we mod 17 by the size of the array, which is 7, and 7 goes into 17 2 times with 3 left over, so that's the result of the mod operation is the 3. So then we would put Andy's value, Andy's website, here at index 3 in the list. Now, a potential problem occurs when you do this hash function in what they call a collision, and that is 2 or more values, 2 or more key values may produce the same hash function value. So if you consider the two strings, tar and rat, they're composed of the same letters. And if you just implemented a simple hash function as adding up the ASCII values of the letters, you would get the same hash value for these two. And so what do you do in the case of a collision? In that case, in this particular bucket or slot at index 6, we would then have two key value pairs in a list. So we can look up index 6 really quickly, but then because there's more than one value there, we have to do a search and match the key value, match the key to see which particular entry in the map that we're looking for. So you can see that the hash map, as long as there are not many collisions, gets closer to a constant time algorithm, constant complexity, what they call order 1, versus a linear search for every key, which is order n complexity. So then the key to trying to avoid collisions, one is you can have a larger array, but that potentially wastes space. The other real key part of it is having a good hash function that doesn't produce many collisions. And there's several that are presented in the section in your book on hashing and hash functions. You can take a look at those. And one of your assignments actually has you try to implement a hash function, and we'll take a look at an example here. Before we look at an example of hashing, let's actually see how we could use the C++'s hash map, or what they call an unordered map. So let's look at an example. So this is C++'s hash table or hash map or dictionary. They call it an unordered map. And so you define an unordered map as a collection of key value pairs. And you can provide it with an initializer list. So you can create the sales with an initializer list. So here the sales for the month of April would be $1,100.50. The sales for the month of May might be something else. And you can also use the subscripting operator to put in additional sales, either change or put in additional entries into the map. And so this map then associates or maps the month of April to the value of 1,150 and maps the month of July to $2,230. So we can create this mapping of string to values using the indexing operation that we're used to, and it essentially converts this string into a number to look up into one of these buckets or lists of key value pairs to find it. Once you've done that, you can then print out the sales for a particular month. In this case, we could actually write a loop for each pair of values in sales. We can print out the sales for the first value in the pair, and that first value is the key value. So we're saying the sales for April are how many dollars. And here we can use some of our I/O formatting. We want to have a fixed number of decimal points and 2 decimal places, and we can look up that first value in the pair in the sales map and get the actual number that we're looking for. Alternatively, because this PR pair is actually a pair that we've seen before, we could also write PR second, and that would give us the value that it maps to as well. So either one of those would work here. It's nice to see this format because then you know you can look up a value in sales by its string name. And so if we run this, we should get a list of sales values for a few months. And the key thing is that we're treating this sales, it looks like an array, but we're able to do indexing with a non-integer type, like in this case a string. And that can be a useful feature. So the next thing we'll look at is a simple hash function. And there are a lot of research that goes into coming up with a good hash function that avoids collisions. Here we'll look at a very simple one that's actually not all that good at avoiding collisions, but it's simple, it's easy to understand. What I've done is just gone to did a search for a random collection of words. So I've got a random list of words here. And then what I'll do is loop through each word and try to create a hash value for it. So a hash function tries to convert something that's not a number into a numeric, or in this case an integer type, so that we can look up into an array. And typically it's some math function that converts it to a number, and then I guess the number could be negative depending on what the function is. So then a lot of times we take the absolute value of it and then mod it by the maximum size of the array that we're using for the hash map. So we could maybe write a function that takes a constant string reference and a maximum size, the n, the size of the array or the hash table, the maximum size of the array or hash table. And then one simple strategy for a hash function would just be to loop through each character in the string and add up its ASCII value. So we can create a sum variable, and ultimately we will return sum mod max size and maybe the absolute value of sum mod max size, because there's a possibility that I guess we could get a negative value if we added up a whole lot of characters. It's unlikely we'd have a string that big, but and then we just can do a range-based for loop for each character in the string, sum up the integer value of that ASCII character. So here we have a simple hash function that takes a constant string reference, so we pass it in by reference so we don't make a copy. It improves performance a little bit. And we make it a constant reference because we don't want to change it. We just want to look at each character in the string. We also pass in the maximum size of the hash table, its current maximum size. We loop through each character in the string and accumulate the sum of its ASCII value, and then return the absolute value of that sum modded by the maximum size. So we'll be sure that we'll get values in the range of 0 to max size minus 1, which are legal indices into the array of the hash table. So then here, inside the loop, where we loop through each word, we can just print out the word and the value that it hashes to. And in this case, we're going to assume we have a hash table with a maximum size of 100, but if we actually implement a data structure, that would be one of the data members of the hash map data structure. And we just print out each value that the word hashes to. And so if we run this, we'll see that decorous hashes to 68 and compete hashes to 49. And here it's interesting, you can see we actually got a collision. So both decorous and whistle, even though they're not the same letters, the sum of their ASCII values produced the same result. The hash function both produced a 68, so we have a collision for decorous and whistle. So that's one of those cases where we would end up having two entries in the same bucket of the hash table. Some of the others, childlike hash to 37 and bored hash to 20, and I don't see any other collisions. So that's actually not too bad to have, 10 numbers or so and only have one collision. And that's where the focus of a lot of research is done in hash functions, is how to come up with a function that gives you the minimum number of collisions, because if you don't have any collisions, then the complexity of a lookup of your hash map key becomes a constant complexity, or order 1, whereas if you have a lot of collisions, then the complexity becomes larger, maybe closer to order n, like a linear search. So here we just looked at some concepts surrounding what they call a dictionary or a hash table or a hash map, or in C++ an unordered map. Specifically, we looked at how to make a simple hash function and how hashing works in a hash table. And also, maybe even more useful, is how we can make use of C++'s unordered map to store a collection of key value pairs.